Okay, so let me now go over the solutions for quiz 6. So given the vector clock of these two events, this is a vector clock of one event and this is a vector clock of another event. I want to find out whether the two events are causally related or not. So the way you do that is compare component wise. So compare 1 with 1, 1 is equal to 1. Then compare 1 with 2, 1 is less than 2, 2 is less than 3. So every integer here is less than or equal to the integer here, and at least in one case, or actually here in two cases, where you have one here is less than the integer here. So we can now say that this clock is less than this clock, so the event associated with this clock happened before this event. Okay, so these two events are causally related. Now compare these two clocks. This 2 is less than 3, but this 3 is less than 2. So we cannot say whether the first clock is less than the second clock or vice versa. So that's why we cannot say whether they are causally related or not. So they are concurrent. Okay, so they're not causally related because we cannot say this happened before this or this happened before this. Actually, they are not causally related, as I say here. So they are concurrent events. Okay, so given this status, the process diagram, space-time diagram, I want you to find out the timestamp of each of these events and then compute the timestamp of this cut and then determine whether it is a consistent or inconsistent cut. Okay, so you start with of course 0 0 0 0 for all these four processes. So there are four processes, so your clocks need to have four entries. So this is a sending event at this first process, so increment this to from 0 to 1, so 1 0 0 0, and this is a receiving event, so you increment for the second slot 0 to 1, and then you take the component wise maximum, so it is 1 with compared with 0 is 1 and then 0 0. Then you're sending from the second process, so increment this 1 to 2 and the rest stay as it is. Now you send to this process. So if you want to compute this, you see that an event happened before this, so you need to compute for this. So let's go to this. Process 4 is sending, so increment from 0 0 0 0 to 1 here for the fourth slot, and you send this, so this is being received, so process 3 increments it 1 and 0 0 0 component wise maximum is 1. So now when you receive this at process P3, you have to increment this to 2 and then take a component wise maximum with this, so 0 compared with 1 is maximum is 1, 0 compared with 2 is 2, and this is 2 now, and then 1 compared with 0 is 1. Okay, you see how I'm proceeding this from left to right. So now you are sending from this process to this process. So this is sending at process 3, so you are incrementing from 2 to 3, so 1 2 3 1, and sending to this process. And so nothing happened before this, so this is process receiving, so increment from 1 to 2 and then take the component wise maximum, so maximum of 2 and 0 is 2, maximum of 3 and 0 is 3, maximum of 1 and 0 is 1. Right, so now let's go to this process which is sending a message to, of course now before this is being sent, so let's send this message. So you have to increment from 1 to 2 and send this message, and then this is receiving this, so process P3 increment from 3 to 4 and take a component wise maximum, 1 and 0 maximum is 1, 1 2 and 0 maximum is 2, so this is 4 and 1 and 2 maximum is 2. So now you are sending from this process to this process, so you are incrementing, this is process 2, so incrementing from 2 to 3, and then this is 1 3 0 0, so sending to this process, so this is process 4 receiving it and increment it from 2 to 1 3, and then take a component wise maximum. 0 and 1 is 1, 0 and 3 is 3, 0 and 0 is 0, 2 and of course you're incrementing to 3. Alright, so then you're sending a message from here. So it's process 2, so 1 3 to 4 and then 1400. So this guy is receiving it. Process P3, so increment from 4 to 5, component wise maximum. 1 and 1 is 1, 2 and 4 is 4, 4 and so of course incremented to 5, 2 and 0 is 2. Okay, so then this process is sending a message. So this is process 4, so 3 incremented to 4 and sending it. And this is P1 receiving, so increment 2 to 3 and then take a component as maximum. Maximum of 2 and 3 is 3. Maximum of 3 and 0 is 3. Maximum of 1 and 4 is 4. So then even though this is sent after the cut, you still go ahead and find this timestamp. So this is process 1 sending, so this is 4, then 3 3 4, and P3 is receiving, so 5 is incremented to 6, and the maximum of 1 and 4 is 4, maximum of 4 and 3 is 4, and this is 5 to 6, and maximum of 2 and 4 is 4. So these are the timestamps of these events. So now this is a cut. So the timestamps of these cuts are, so this is process 1, the latest timestamp before this cut is 3334, so that is the timestamp of process 1. At process 2, the latest timestamp before this event is 1400, so that's what I process at P2. And at P3 it's going to be 1452. At P4 it's going to be, before this is this one, so 1303. So if I take a component wise maximum, this is maximum of 3 1 1 is 3, maximum of 3 4 4 3 is 4, maximum of 3 0 5 0 is 5, maximum of 4 0 2 3 is 4. So now we look at this. This 3 came from process 1, this 4 came from process 2, okay, this 5 came from process 3, this 4 came from process 1. So the entry corresponding to process 4 actually came from the timestamp or vector clock of process 1. So that means it is inconsistent, which means process 1 knows more about process 4 than process 4 itself, because process 4 knows its timestamp is 3, whereas process 1 thinks process 4's timestamp is 4, this entry. And that actually corresponds to this thing, because you see here the sending of this message, right, is it's not recorded in the global state because you're capturing the global state here. So the sending happened after you record the global state, but here you're recording the receiving of the message before recording the global state. So you have a state where the sending is not recorded whereas the receiving is recorded. So that's like an orphan message. So we call that as inconsistent cut. Okay. Now for the Lamport's mutual exclusion algorithm, remember there are two Lamport algorithms actually. Chandy-Lamport is for the global state recording. So some people have answered for that, so you should not answer that. This is a mutual exclusion algorithm. You're trying to access a critical section. So if you look at the course website, I have recorded a lot of videos on all these things, and so you have to look at this video where I talk about the Lamport's mutual exclusion algorithm and analyze its properties with respect to safety, liveness, and fairness. So again, what safety is, only one process should be able to enter the critical section at any point of time. In Lamport's algorithm case, a process has received the reply message from every other process, and this process's queue request has to be in the front of the queue at the local process. At the same time, even at every other process, that process request will be in the front of the queue. So only one process can enter the critical section at any time. That process which has received the reply from all the message processes as well as its own request is in the front of the queue. Now for the liveness property, if a process has made a request, then that process will get access to critical section at any point of time. And the reason is here the process's requests are ordered in the increasing order of timestamps. So if a process has made a request, the request is going to progress in the queue in the increasing order of timestamps. So its and if a process is done with the critical section, it's going to send the release message to the other processes. So the other processes are going to get access to critical section at some point of time. And again, since accesses are given in the increasing order of timestamps, the processes are going to access the critical section in the order in which the requests are generated. So it's going to guarantee you fairness. Okay, so go through that example. So same thing with Ricotta-Agarwal algorithm too. So as I said, there may be a good chance of you being tested on Ricotta-Agarwal in the next exam. Okay, all right. Now the matrix algorithm. So here we want to send so from process 2 I'm sending a broadcast message to process 3 and process 1, and after process 3 receives this message, it sends a broadcast message to process 1 and 2. So you can see here this message is reaching first, and then this message reaches process 1. So you have to think about it. Okay, so let's see, you start with 0 0 0 for all the processes, and then in the matrix algorithm what you're trying to do, you're incrementing while sending, and you're not incrementing and doing anything while receiving. Okay, so process 2 is sending a message to process 1 and 3, so you're incrementing this entry. Second row corresponds to process 2, and you're increasing the columns. For process 1 you're sending a message, and for process 3 you're sending a message, so incrementing to 1 in each case. And then when you receive, all you do is take a component wise maximum. So this is all zeros, so take a component wise maximum, you get this. So now you are sending a message from process 3. So you're sending from process 3, so third row you're sending to process 1 and 2, so incrementing for 1 and 2, 1 and 1, and sending to process 1. And when process 1 receives this message, it has to compare its clock or matrix timestamp, which is this, with this. So what this means now, for process 1, the message is received, you have to check the first column. Okay, so process 1 looks at the first column in the message it's being received and its local matrix timestamp. So this column indicates the number of messages that process 1 should have received, and this is a message coming from process 3, so that's why this is a 1. But this second one, this one, the second row, this one really indicates that process 2 has sent a message to process 1, but process 1 has not yet received it. So process 1 has received that message which process 2 has received, so process 2 has sent to process 1, and process 3 has actually received that message before sending this particular message. That's why process 3 has recorded the sending of that message by process 2. So which means the message that process 3 generated was sent after receiving the message sent by process 2. So which means process 1 should get that message that process 2 sent before receiving and processing this message from process 3. So that's what is meant by causal delivery of messages. So process 1 basically waits until it gets this, and this message comes with this timestamp. So again, for process 1, nobody else has sent anything according to this message, so process 1 can accept this message, take a component wise maximum, and at this point this message could be delivered, because if you compare the vector clocks, this is going to be only that corresponds to process 3 sending the message to process 1, and process 1 has received the message from process 2. So you can get this, and you take a component wise maximum, that gets you to know about this. Okay, component wise maximum of this and this will get you this. So now process 1 learns about process 3 sending a message to process 2. Okay, and this message also goes to process 2, so process 2 has to just basically take the component wise maximum of its own clock or matrix timestamp with this. And now process 2, when it receives this is the entry for process 2, right? And it compares this with this. Process 3 sending this message to process 2, other than this, process 2 is not expecting, should not get any message, right? Because nobody has sent any message to process 2. So that's why process goes ahead and accepts this message.